Hi everyone. I hope you had a great Thanksgiving break. I am here to show you some notes about section 1.8 on inverse functions. So you're going to watch this video today, and on Friday when you're in class, I think Mr. Wilson will come over and answer some questions for you. So you're going to have an assignment, and I'm going to give you the assignment at the end of the video today, and then it's going to be due at the end of class on Friday. Okay, so don't wait until Friday to do the assignment because it's pretty lengthy, but be working on it, and then if you have some questions, and then you can get it finished up and upload that assignment by the end of class on Friday. Also, while you're taking notes, when I'm doing a video like this, just know, and I hope that you know, I've pre-written a lot of them, except for any examples that we're going to do, because you can pause the video and get things written down as you need to. So just know that's why I'm moving pretty quickly through it, just to kind of limit the amount of video time that there actually is for me to upload and process and everything with YouTube. So we will get started with talking about inverse functions. I'm going to see if I can get that to, it's good. So inverse functions are functions that undo each other. This is the technical definition that we have in the textbook that just says let f and g be two functions such that f of g of x, so a composition, is equal to x, and also g of f of x is equal to x. So no matter which way we do the composition, they both come out to be x. Then we would say that the function g is the inverse of the function f, and it's denoted this way, this f with a little -1. That is not a -1 exponent, meaning move me. Okay, this is the inverse notation. A lot of times you'll see it written this way, f with that little -1 with the x. And we read that the inverse of f of x. Then what we're saying by this statement is f of the inverse of f of x is equal to x, and the inverse of f of x is equal to x. The domain of f is equal to the range of f, the inverse of f, and vice versa. Okay, so the domain and the range switch. So the first thing that we're going to do is this problem. Show that the functions are inverses of each other. We have f of x is 4x minus 7. We have g of x is x plus 7 divided by 4. In order for us to show that they are inverses, we have to show that f of g of x is equal to x and g of f of x is equal to x. So I'm going to start with f of g of x. That's f of x plus 7 over 4, which says go to the function f, here it is, and in place of this x, we're going to put x plus 7 over 4. So I'll have 4 times x plus 7 over 4 minus 7. But we can then quickly see, and you're going to notice this a lot when we're dealing with inverse functions, that those reduce. So we have left over then x plus 7 minus 7, and x plus 7 minus 7 is x. So that one checks out. We also have to check g of f of x, or in this case, g of 4x minus 7. Or I'm going to go to the function g now, and in place of this x, I'm putting 4x minus 7. So I'll have 4x minus 7 plus 7 all divided by 4. But 4x minus 7 plus 7 is just 4x divided by 4. 4 over 4 reduces to just x. Okay, so we can write our final statement down here. So f of x and g of x are inverses of each other. Okay. All right, but how do we find an inverse function if we don't already have a function given? Here we go. So we're going to have a few steps that we can follow. There they are. Finding the inverse of a function. We start with replace f of x with y. Then we'll interchange the x and the y. We will solve for the y value now, getting y by itself. Then we're going to replace y with the inverse function notation. and then we would verify it by showing that f of the inverse of f of x is equal to x, which is equal to the inverse of f of x. Okay, so we'll do a few examples here. We'll start with a fairly straightforward one. F of x equals 2x plus 7. I'm going to begin by writing this as y equals 2x plus 7. Now I'm going to interchange x and y. So I'm just going to switch their locations. So now I'll have x equals 2y plus 7. And then we need to get y by itself. To do that, I might subtract 7 on both sides. So I have x minus 7 equals 2y. And then we would divide both sides by 2. I'm going to rewrite this as y equals x minus 7 over 2. Or we would use our inverse function notation. The inverse of f of x is x minus 7 over 2. Squeeze that on there. Okay. Then in order for us to verify it, we have to do two different compositions. So I might say I'm going to check them over here. So I need to do f of the inverse of f of x. Or in this case, f of the inverse, which is x minus 7 over 2. And I go back to that original function. I'm going to have 2 times x minus 7 over 2 plus 7. Or x minus 7 plus 7 when these 2's reduce. We're just x. So that one works. So that's a check. Yes. And then we also have to check the inverse of f of x, or the inverse of f of the original function 2x plus 7. And this should feel very similar to that first problem we did. We'll go now to our inverse function here, and in place of this x, I'll put 2x plus 7. No, it's minus 7. Ooh, this is a marker I can't erase. Plus 7, I'm going to do this. Minus, divided by 2. 2x minus 7 plus 7 is 2x. 2x over 2 reduces to just x. So this is, in fact, our inverse function. Okay. We can do another example, number 2. Let's do f of x equals 4x cubed minus 1. And I need to move this. There we go. So we have 4x cubed minus 1. Again, I'll rewrite this y equals now 4x cubed minus 1. Then I'm switching the x and the y. So now I'll have x equals 4y cubed minus 1. And we will solve this for y, or get y by itself. I'll add 1 to both sides. So I have x plus 1 equals 4y cubed. Divide both sides by 4. That will be the first thing. So now we have x plus 1 over 4 is equal to y cubed. And the way we get rid of a cube is to cube root. But I have to cube root this whole thing. So I have y equals the cube root of x plus 1 over 4. And we could write that with inverse notation. We think that this is the inverse. We still need to verify it by showing those two compositions. So I'll come over here. This is where I'm going to check them. We'll start with f of the inverse of f of x, or f of the cube root of x plus 1 over 4. So now here, in place of x, I'm putting this cube root. So I'll have 4 times the cube root of x plus 1 over 4 cubed minus 1. Well, this one's interesting because a cube and a cube root will undo each other. So I end up with 4 times x plus 1 over 4 minus 1. And again, then it starts to feel very similar to ones we've done already before. Reduce the 4's. X plus 1 minus 1 is just x. So that one worked out. Then we would have to try f of the inverse of f of x, or the inverse of f of x. I think I said that wrong. And we'll have the inverse of f of 4x cubed minus 1. Or I go to the inverse, and now in place of this x, I'll put 4x cubed, so I'll have the cube root of 4x cubed minus 1 plus 1 all over 4, which is really just the cube root of 4x cubed over 4, but the 4's reduce to give me the cube root of x cubed, which is in fact x. So that checks out, and then we can know that this is in fact our inverse function. Our third example of finding the inverse f of x equals 3 over x minus 1. Again, we start with y equals 3 over x minus 1. We will interchange the x and the y, so x is 3 over y minus 1. And now we need to get rid of, or we need to get y by itself. Be careful, you'll run into some problems like this. The first thing we need to do is actually add 1 to both sides. So we have x plus 1 equals 3 over y. We can't keep y in the denominator and have it be solved. So I'm going to multiply both sides by y. When I do that, though, I need some parentheses. So I have y times x plus 1 is equal to 3. And then to get y by itself, we'll divide by x plus 1. So y equals 3 over x plus 1. Or I'll use my inverse notation. The inverse of f of x is 3 over x plus 1. Now, we still need to verify that. So I'll come over here. Let's maybe make a little line across there. So I need f of the inverse of f of x, or f of 3 over x plus 1. This becomes kind of interesting because now what I have when I go here back to the original function is 3 over x plus 1 minus 1. But remember, to divide by a fraction, we would flip by or multiply by the reciprocal. So this is really 3 times x plus 1 over 3 minus 1. And again, we're back to something very similar to what we've seen before. The 3's reduce, x plus 1 minus 1, which is just x. Okay? And when we go the other direction, the inverse of f of x, or the inverse of f of 3 over x minus 1. This one's actually a bit simpler because we'll have 3 over x minus 1 plus 1. Okay, again, going back to here, and in place of this x, I put 3 over x minus 1. I could even put that in parentheses if it'll make it easier. But minus 1 plus 1 leaves me with just 3 over x, or 3 times x over 3. Remember, when we divide, multiply by that reciprocal, the 3's reduce, leaving me with just x. So we did, in fact, verify that this is the inverse function. All right. Next. Not every function has an inverse. Okay, this page is full of a bunch of just notes. I think we can, let's see, squeeze that this way. There we go. Not every function has an inverse. Take, for example, f of x equals x squared. If we make it y equals x squared, interchange the x and the y, and then solve for y, we end up with y equals positive or negative square root of x. But recall, in order for an equation to be a function, each input value, which is x, must have one output value, which is y. For y equals positive or negative square root of x, we would have 2 y values for each x value, right? If I put 4 in place of x, I would get positive 2 and negative 2. Therefore, y equals positive or negative square root of x is not an inverse function. In fact, in order for a function to have an inverse, it must be what we call 1-to-1. Each input value must have a distinct output. Okay, so now not just that it has one output, but that it has a distinct one, different from all others. We can use the graph of a function to determine if it has an inverse. to do this, we use something called the horizontal line test. This is very similar to the vertical line test, only now it's a horizontal line, so it's going this direction. Recall, vertical line test determines if a graph is a function. Okay, so we'll look at some graphs down here. I think we can see that okay. All right, so we're going to determine if the functions graphed below have inverses. So we'll look at this first one. I would notice that I could use the vertical line test. It is a function, but I'm using the horizontal line test to determine whether it has an inverse. Because this horizontal line touches it in more than one location, this one does not have an inverse. You might recognize this as an absolute value graph. Okay, absolute value graphs don't have inverses. If we look at the second one here, again, we could use the vertical line test to see that yes, it is a function. We can use the horizontal line test and we can see that it never touches that graph in more than one place. So this one also, well, this one is a function and it has an inverse. On the next one, again, we can use vertical line test to see that it is a function. We can use the horizontal line test to see if it has an inverse. It does not touch that graph in more than one place at a time. So this one does have an inverse. And lastly, way over there, number 4, again, this is a parabola or a quadratic function. We know that it's a function. However, when we use the horizontal line test, we can see that it touches that graph in more than one place. So this does not have an inverse. Okay, well, let's talk about other things with graphs. There we go. Inverse functions switch the domain and the range. We said that in the definition. Therefore, the graph of an inverse function is the reflection over the line y equals x. To graph, we're going to find several points, then we're going to interchange x and y values and then graph them. So domain, again, representing x, range is y. If the domain and the range switch, it makes sense to take those ordered pairs and to switch them. So a function is graphed below, here it is, and I would like for us to graph its inverse. So I'm going to note some of the points from it. I have 3 points in particular. I've got -2, -2 down here. Here I've got -1, 0. And here we've got 1, 2. And if we want to find their inverse, we would switch them. Well, this first point is kind of interesting because the x and the y values are the same, so nothing changes. But the second point, now we're going to be graphing 0, -1, and this third point we would graph 2, 1. So on this graph, I've now graphed that original one, but I've used dashes to represent it. And now we're going to graph the inverse function, -2, -2. So that point is the same. Now I have 0, -1, so I have a point here, and I have the point 2, 1, which is here. So now this is graphed like this. And there is the function graphed with its inverse. Okay, the last thing we need to talk about is that we can find the inverse of a function like y equals x squared if the domain is restricted. So we can't find it just of y equals x squared. We already talked about that. But if we restrict the domain, then we can. So we have this problem, f of x equals x squared plus 1. But now it says x is greater than or equal to 0. So only the right side of this parabola is what we're talking about, right? We have this function, but this tells us that we're only looking at the right half of it, okay? We can see from the graph that this restricted function now has an inverse, right? We have to use that horizontal line test, and because I'm only looking at half of the parabola, it now has an inverse. So we'll go about finding the inverse, similarly to what we did before. So we're going to change the f of x into a y. We're going to interchange the x and the y, so x equals now y squared plus 1. Then we will solve for y, so I'm going to subtract 1 on both sides. and then I need to take the square root of both sides. Now, I'm going to go ahead and write it this way, plus or minus the square root of x minus 1, because when we take the square root of both sides, we get two answers. However, okay, since the graph is restricted, to the positive side, we will only take the positive square root. Make sure that you're able to see all that, okay? So then we'll say that the inverse of f of x is only the positive square root of x minus 1. Now, note, if the graph had been restricted to the left side, we would have taken the negative square root. Okay, so if the original problem had said x is less than or equal to 0, then our inverse would have been the negative square root of x minus 1. Okay, hopefully that will make sense. Okay, your assignment for this section is on page 254. Right, there are copies. You will get a copy of this. You're going to do 2 through 52 even. Again, I know that that can be quite a bit. However, this is not due until the end of class on Friday. So you have the rest of the time today to start working on it. Obviously then tomorrow. And then on Friday in class, Mr. Wilson will answer some questions for you. And then you should plan to be able to finish that assignment and upload and submit a photo to Canvas on Friday by the end of class. Okay. All right. That is all that I have for you. Let me turn this back around. And I hope that you're having a good week. And I will plan to see you on Tuesday. Have a great day.